In part 2, it might not be as obvious that the integrals are improper. So you see that neither bound has infinity. What we will see, though, is that the integral from 0 to 3 passes through 1, and 1 is a point of discontinuity of the function or the integrand. So what we're going to do first off is we're going to rewrite this integral placing one of the bounds to be that point of discontinuity. So we'll go from 0 to 1, x minus 1 to the 2/3 plus 1 to 3 dx over x minus 1 to the 2/3. Okay, so for each one of these, we have to write a separate limit definition statement. So let's start with the first one, the integral from 0 to 1 of dx over x minus 1 to the 2/3 equals, it's a limit now, and this limit is going to be the integral from 0 to b. But as you see, we're going to be approaching b from one side. We're going to be approaching b, we're going to be approaching 1 from the left-hand side. So that's the limit statement, and the integrand is the same. Okay, so now we're going to integrate and carry our limit statement. Limit as b goes to 1 from the left. It's very important that you show the one-sided limit. The integration of this is 3 times quantity x minus 1 to the 1/3. And employing the fundamental theorem from 0 to b, which will give us the limit as b approaches 1 from the left of 3 b minus 1 to the power of 1/3 minus, when I plug in the 0, I get 3 times negative 1 to the 1/3, and that expression is the one I'm taking the limit of. And you can see that if I plug 1 in here, it makes this expression go to 0. It makes this expression go to 0, and then I'm left with a constant, and that constant is 3. Let's do the next one. The integral from 1 to 3 dx over the quantity to the 2/3 power. This time, we're going to write the limit, and we're going to go from a to 3, because a is the 1, the point of discontinuity. And we're going to say that a approaches 1, but from one side, it's going to approach from the right-hand side. So that's really important that we write it as such. And again, this is x minus 1 to the negative 2/3. That could just help us integrate it better with respect to x. So this is the limit as a approaches 1 from the right. The antiderivative is 3x minus 1 to the 1/3. And again, fundamental theorem, we're going to take that from a to 3. Limit, a approaches 1 from the right. We plug in the 3, and we get 3 times 2 to the 1/3 minus 3 a minus 1 to the 1/3. Okay, and this limit, now as we approach 1, we see that this expression goes to 0, and then we're left with the constant, which the constant is 3 times 2 to the 1/2, or 3 times the square root of 2. So now if we go back up to where we started, we can clearly see that the answer is going to be the sum of the two respective limit statements, improper integrals we just found. So 3 for the first one, 3 radical 2 for the second one, and that constitutes our answer to example E. Now for example F, I've already drawn the original integral here, and I've separated them into two, splitting them by the point of discontinuity, the reason that it makes an improper integral to begin with. So like we did in the last example, I'm going to look at the first one and add them up as necessary. So here we have the limit as b approaches 3, respecting the side, it's approaching from the, actually it's going to be approaching from the left, that's right, approaching from the left. Okay, of the integral from 0 to 3, I've written it as x minus 3 to the negative 2, makes it easier to integrate. And so this is the limit as b approaches 3 from the left, the antiderivative negative 1 over x minus 3, and fundamental, we take that from 0 to b, which equals the limit as b approaches 3 from the left, and we have negative 1 over b minus 3 minus a minus, so plus positive 1/3. There's our new statement that we have to find the limit of. Okay, so it's approaching from the left, so it's approaching 2.5, 2.9, 2.9, 2.9999999. As we plug those in, this denominator is going to be negative, but getting really close to 0. So that tells us that we are going to have negative over negative positive, and 1 over that positive really small will give us infinity. So you would say the minute you have infinity, infinity plus 3, infinity minus, doesn't matter. Infinity is unbounded, infinity doesn't exist. So the minute we get infinity in the problem, unless it's infinity over infinity, the minute we get infinity in the problem, it goes to infinity, which means that this portion diverges, this integral diverges. And then the minute you get it one part to diverge, the entire thing will diverge. Even if one half was infinity while the other half was negative infinity, it doesn't matter, they don't cancel each other out. Infinity plus negative infinity still does not exist, it's divergent. I do not have to do the second one. I got infinity, I know the answer is does not exist or approaches infinity. Final example, G, the integral from 0 to 1. We recognize that the point of discontinuity is not inside 0 to 1, but the point of discontinuity is one of the bounds itself, the 0. So we still approach it the same. Equals the limit as a approaches that 0 from the right-hand side of a to 1 of x to the negative 1/2 dx. So fairly straightforward. We have the limit as a approaches 0 from the right, the antiderivative 2x to the 1/2, and we take that from a to 1. That's going to give us, when we plug in the 1, it's going to give us 2. I'm just writing it now, distributing the limit, if you will. And then the second portion is going to be 2a to the 1/2, but the a is approaching 0 from the right, which gives us 0 for that second term. 2 minus that 0 is 2. So we say that the integral, the improper integral here, converges to 2.